All right, so go ahead and start here in a moment. Buonasera. Good to see everyone. All right, and welcome to Optimization Design Patterns. My name's Mike Shah, and it's great to see everybody here. Thanks for welcoming me, the Italian C++ community. And we're going to have a little bit of fun today talking about optimization. This is an introductory level talk on optimizations, but if you have some more advanced folks and want to point out some things, feel free to. I'll show some code and the slides will be available as well. So if you miss something on the code or if I go through something fast to balance time, don't worry about that. We'll be able to check the slides later on. All right. So again, just a little bit about me. I'm a teaching faculty in Boston, USA, but I like to travel abroad as often as possible. I do various training, mostly in C++, and of course lecture on topics like computer graphics and these sorts of things. So feel free to check out YouTube, free courses I have, all these sorts of things, if you enjoy this talk. And as I mentioned, here's the code for the, or the repo for all the code that's going to be shown later, so feel free to check that out. And of course, you've read the abstract. That's why you're here. You got excited about this talk. But just to kick things off, I have a question for you folks. Just to see how many of you have heard this phrase, probably the most famous phrase in optimization. Somebody's already got their hand up. I think they know what's coming here. That's this. Yeah, raise your hand if you've heard this. Almost every hand's going up here. So premature optimization is the root of evil. Or at least for most of programming, by Donald Knuth, a Stanford professor, computer scientist, who's done a lot of seminal work in computer science. Now, my second question, though, is how many of you have actually read the paper which Donald Knuth has stated this? Yeah, some hands are going up. Yeah, great. The paper, I believe, is about 50 years old, so it's run its course, but it's still relevant today. And I'll show you some quotes or read them off for you. So this part here that I have highlighted, again, it's small text, is the premature optimization is the root of all evil. But of course, you can see there's a lot of different text around it talking about probably interesting or relevant stuff, right? We have to have context when we quote something. So again, this is from the paper Structured Programming with Go-To Statements. So again, Go-To, very controversial back in the day. Probably still a little bit controversial if you use it. But the very next sentence here says that yet we should not pass up our opportunities in that critical 3% for optimizing our code. Okay, so there's a little bit more discussion here. There's a little bit more. That quote always gets chopped off just a little bit too early. And I thought there were also some interesting notes here, which I'll read for you. 2 sentences later, where Knuth says, it is often a mistake to make a priori judgments, so sort of guessing ahead, about what parts of a program are really critical, since the universal experience of programmers who have been using measurement tools has been that their intuitive guesses fail. So oftentimes when we think about, oh yeah, this will make code faster, I heard this in that talk. Or everybody says, no, don't do this, or never optimize it. The compiler will fix it. All these different things. Again, we have to measure if we know if an optimization is going to work. So I always sort of tell my students here, when we see this quote here, the premature optimization is the root of all evil, sure. And it's potentially bad, especially if you're facing a new challenge and don't have years and years of experience. But never optimizing again when there's opportunities available is also evil. So that's paraphrased. Other folks have said that. That's where I've heard it from. So that's a little bit of a guiding principle for this talk on optimization, to just kind of think about the code we're writing, where we can improve it. But you're going to find that optimization is tricky, and perhaps that's the takeaway from my talk, meaning that I named this talk Optimization Patterns, but really I should have named it Optimization Strategies, Optimization Trade-offs, or this works sometimes if you do X, Y, and Z. Might have been a better name for this talk. Yeah. So again, from Knuth in this paper. I'm going to give you some homework to actually read this for some of those who haven't read this. Again, another quote here saying, a methodology of program design, beginning and reading, a methodology of a program design beginning with readable and correct but possibly inefficient programs that are systematically transformed, if necessary, into efficient and correct but possibly less readable code. So again, the classic computer science trade-off is space versus time. I'm going to talk about that a little bit. But sometimes we're also writing code. Maybe we're getting really into template meta programming. Maybe we're doing something that's going to make it a little bit harder for someone to read, maintain, or do that optimization. So there's always a trade-off somewhere when we're optimizing. So again, that's my takeaway here. And in the long term of a project, and again, we've seen lots of talks already, which have been wonderful with game dev and other applications where my background sort of is where this is very applicable, is sometimes we just need to write the simplest code and that'll sort of optimize itself, or over time as we iterate we can apply some optimizations. So again, we'll find optimization again as an iterative process in our code base. And we really have to know not just code and the tricks, but the hardware as well. So some of the patterns I'm going to demonstrate, again, the examples are relatively simple today to fit on a slide so we can talk about them. But they still might obfuscate or complicate the code in ways that you might deem unnecessary, or for the long-term readability or maintenance of a project if you have lots of different developers with different levels of skill. So as I mentioned, CPU is really important to understand, the actual hardware in the architecture. So if your hard drives, CPU systems, and so on. I've compiled a list here of what I think are very excellent talks on various computer architecture. So folks like Scott Myers, Andrei Alexandrescu should be on that list, Emery Berger, et cetera, et cetera. All these folks have really good introductions of, again, why it matters to understand your hardware. So again, on the slides, you can take a look at that list later. I'm going to talk about this just a tiny bit, but again, this isn't really going to be a talk on compiler optimizations, although you'll see me pull a few things out for actually writing our code. Because again, sometimes we don't want to just trust our compiler to optimize something. But what is interesting if you do read through and learn about some compiler optimizations is the different themes you might see. Again, they're compiler optimizations because some compiler writer said, hey, there's a common theme here. There's a pattern, and we're going to try to automate that to the best of our ability. So again, compiler optimizations, interesting to know about. We'll look at a few as we go along, but not the focus. So again, our goals for today is to just kind of give you a grab bag of optimization design techniques or strategies that you can apply. I try to give it a flow, but at some points we'll grab and choose some things that might be interesting for you to just try and measure. And the reality is, as I was writing this talk, I came up with some micro benchmarks, ran them, so you might get different results. But again, you always have to validate, you always have to measure. And what I ended up finding, again, when you have optimizations, or are going to talk about them, you better talk about what your strategy was to measure things as well. So I'm going to show you a little bit of profiling if you haven't done that. So how to measure your code and what those sorts of things might tell you, or what might be interesting to know about. All right, so with that introduction in mind, to talk about some optimization patterns, or again, strategies or trade-offs when it comes to optimizing. I'll give you a few different techniques or a quick kind of run through, and you'll just have a bunch of, again, call them blueprints or recipes that you can run through and try on your code. Again, how to formalize this. We don't, I know some folks have this with the design patterns, if you've seen the Gang of Four books and these sort of things, names for these optimizations. But again, I've tried to find ones that have names and aren't necessarily just kind of bit hacks. So let me summarize a few of them for you. I might run through the next few slides a little bit quickly running through some examples, and then we'll get through a use case of iteratively optimizing some code. And another great reference for writing efficient programs, again, it's one of those books that's escaped for a long time, being more than 20 or so years old, well over 20 years old, I think it's 1990. It's from John Bentley. Has anybody learned or seen Bentley's rules before? Some of you folks have. You might have seen it. Where I learned about it was MIT's performance engineering course, and then I taught another one modeled after it. A really great list of talking about how to get performance out of your programs. So I want to go a few of these patterns that Bentley finds, things that are interesting. So again, when we're going to talk about optimizations, we're usually talking about trading something to get something else. So memory for time or space for time, time for space. Again, maybe space is the more premium resource. And sometimes you can get both space and time if you're lucky. And that's sort of the optimal optimization. Most of the optimizations I'm going to talk about are for runtime, making things fast. But again, occasionally you want space. So the classic sort of optimizations that you can make, space for time here, are with things like if you have a singly linked list, you, for instance, might have some data structure that looks like this with a head, and you can iterate to the next node by effectively linking the pointers together. Now, of course, if you're going to append to this linked list, you've got to iterate through the whole list every time in this first iteration on the top. And that's going to be expensive, O of n to append to the end of the list. Okay, meaning that we have to traverse through every single node as we go on. But you can do this much more cheaply, trading a little bit of space by adding a tail pointer that logs your tail, and then you can reach the end of your linked list in O of 1 time, okay? Constant. Okay, so that's sort of the classic linked list optimization, or an example of trading space for time. There's other nice modifications we can make for space for time. Again, a classic example. For those of you who have probably computed some Fibonacci number, it seems to be the classic, like, I don't know, first year assignment or something you wander into. You know, doing this the recursive way is 2 to the n. It's a very exponential time here. In fact, I ran this program here where I'm computing the 45th Fibonacci number, and it took 10 seconds. Okay, so it takes a little while. We'd like to speed that up. So again, what's our strategy? Well, it's too slow, so what can we trade? We can try to trade space. So the way to speed this up, and again, as I'm flipping through these, don't worry about reading the code. I know it's small. That'll be for later. The basic idea is as you compute each Fibonacci number, you can store or memoize that Fibonacci number. Okay, so in that way you don't have to recompute and reduplicate work. And the drum roll for this result, just to inspire you, is we're looking at 0.02 seconds versus 10. So much, much, much faster by trading a little bit of space for time again. Okay, so we're just seeing some themes here. So we can also modify or alter our data. So again, trading some time for space, and sometimes we benefit in both areas. For example, if we're compressing our actual data. So again, if we have a big piece of data, we might zip up that data. If we need to pass it back and forth, it's cheaper to pass a smaller piece of data around. Okay, that's why we zip things up. It's less file blocks, less files to transfer, and so on. There's other just pragmatic tips about using the right data type for the right thing. Again, I see this all the time in computer graphics, where if you're storing red, green, and blue colors, and you only need a value 0 to 255, right? You use a uint8t or a char, unsigned char, and depending on what you're using, not a full integer. Okay. Some other trade-offs, time for space. This is just looking at, interpreters. I know we're C++ here, but Python's an example of that, right? We're trading time in a sense because, well, we don't have to. For those who are in that last talk listening about long compile times, right? We can just run instantly. but we are going to trade time on the actual performance. Okay, some examples there. Some other things that we can do, modifying our data for space and time. We can do bit packing. So essentially that's saying, well, if I've got this structure here and I want to store the actual day, so the year 2023, the month June, so 06, and the day 10 here, I actually don't need an integer to ever store any value there. I mean, hopefully we'll get to the year, 2 billion or whatever. But, at least for our current date, right, we only need 13 bits, 4 bits for a month, 5 bits for a year. Again, depends on your calendar system, I suppose, but it is a difference of a 96-bit data structure on the left versus 22 bits. And again, for my compiler folks, this might get rounded up to 32 or whatever, but we're still saving a lot of space there. Okay, so packing our data and being efficient. So the question. Yeah, so the question was, couldn't we have just used a smaller data structure, just use a char or something here? Sure. So we've got char, that's 8 bytes for each, 24 bits. I guess I saved 2 more bits doing that, but it'll get padded most likely for alignment. But yeah, certainly those are the types of things we do. We just want to think about this stuff, right? But how will we know to think about this? Well, that's where I have to show you how to profile in a moment and try to find performance areas. Okay. Other questions on this? Folks are going to have trading space for time stuck in their head and vice versa, I hope. All right, so there's some other interesting things. And again, depending on what industries you're working on or where you're at in your career, if you're able to operate on one piece of data and perform the same operation, these are single instruction, multiple data. Or again, I just have some block of data here, and I'll point with my laser pointer here. And if I'm just adding 2 arrays together, it's sort of the classic example, I could do that in parallel. Okay, and we have this on our CPU, or I can do these GPU operations as well. Okay. All right, so that's a little bit about modifying the actual data, being more efficient, packing our data together. And we can sort of, get into this sort of bit counting routine and seeing how small we can pack things together or managing time. But there's other things we can do, like actually modify our code structure. So this is getting a little bit into what our compilers are good at to try to make things more efficient. So let me go ahead and show you just a few examples so we get the idea. So here's a optimization known as code motion. And the basic idea is, well, maybe I'm doing some work over and over and over again. So I'll read off what's at line 15. I'm doing this 2 times, this approximation of pi. I had to give myself just a little bit of work here to do. But we're doing that over and over and over, recomputing this value. That's just going to be the same thing over and over and over. Okay. So what the compiler will do is hoist or move out that code from the loop here. Okay. Or we could do that, right? Sometimes our compilers are good at doing that, but we could also do that. And the idea is we should get more performance. There's less instructions being executed. We've effectively saved the value, pi times 2 in this variable here, so we don't have to keep doing that function call and so on. Okay, everybody comfortable with that idea? So sort of caching or saving that value. All right, now I did actually run this as an experiment here, and you'll see that the experimental results are inconclusive. Maybe this is too small of a program. That's probably part of the problem, right? It can be a little bit noisy to measure something that runs so fast. But what could this be? Again, I told you things aren't going to be so simple. That's why we have to measure and run some experiments. So the left side, which I claimed was unoptimized and not doing this cool code motion thing, ran in 0.009 seconds. On the right side, it's actually slower, running in 0.019 seconds for the real time. And the CPU time is also slower. Well, again, we've modified the structure of our code, but again, this is where we have to go back to that slide and watch those 5 talks about our computer architecture. Because even though we're storing some value somewhere, well, that means we have to look up that value in memory. Have folks in the audience heard about us being I/O bound and that being a performance problem? Just kind of gauging. I'll just leave it as a, I saw some hands go up. I'm going to leave it as a key insight for later. Okay. All right, so the rest of this sort of modifying code structure things are, again, giving yourself sort of early exits, little ways you can, again, micro optimize things by basically writing a little bit more efficient code, meaning giving yourself an early termination. So if you find the value that you're looking of on this left side where you're looking for the index of some value, you don't have to wait till the end of the code to just return it, right? You can return and end early if that's the job of the function. Okay, so again, going to save you CPU cycles. Okay, so a few more sort of examples of that. This one I want to talk about because I'm going to bring it up again shortly, is this idea that you can unroll your loops. Okay, so what does this mean to unroll our loops? Well, when we first learn about loops in programming, we probably learn about it as a way to repeat a lot of work, right? And sort of monitor how a program is going to execute. But if we think about what the computer is doing, if we just play computer for a moment, in this loop here at line 9, we're looking at this condition, we're jumping down a line, then we're saying, oh, we got to jump up somewhere else, okay? So we're kind of jumping around where we've got to execute. And that means the computer is doing some thinking. It's doing a test every time on this condition, I less than 4. So wouldn't it be nice if we could sort of just unroll this loop and make things a little bit less hard so we don't have to jump somewhere else, okay? We just unroll the loop and do 2 iterations of what we're adding, okay? And oftentimes that can also enable some other compiler optimizations, but this is kind of a neat trick, right? We've removed our abstraction of a loop because maybe we don't need it, right? That's a really small, we're summing 4 elements, right? Why not just sum all 4 and then there's no guesswork about where we're jumping, okay? So that's the idea. Okay, these other ones, fusing your loops and again, just trying to simplify your code, things your compilers can do. And then some other, things like picking better instructions for various operations. And then some other things I think we pick up in our careers, things like early exits. So for instance, if I'm trying to test if these 2 circles are colliding with each other, I could actually, again, give myself an early exit by saying, well, if the x values are really small, sorry, if they're greater than the radius, then we must not be colliding. Okay, so there's some little ideas like that. Okay, and then finally, some other important optimizations, inlining. This is the idea that you essentially just get rid of the function call because the compiler or maybe you are giving a little hint here and saying, well, if I'm just adding and if I'm doing this subtract or whatever here, why don't I just embed the body of that code here? Because it's really tiny and small and it'll fit there. So I'm going to trade a little bit of space, making my program a little bit bigger for a little bit of time where I don't have to jump to some other function. Okay, that's the idea of inlining. All right, and then just some other rules for simplifying our code. If we can evaluate it, just evaluate right away. Okay. So anyways, I'm going to flip through some of these. This one becomes particularly important. I actually just gave another talk about this, but const expr, and it's going to be related to what we do with templates later on. How many folks are using const expr these days? All right, yeah, const expr everything. It's kind of the saying. Of course, we are trading something though, right? We're trading compile time, which is another one of our trade-offs for, potentially more space on our program and faster runtime. All right, so with that kind of crash course introduction of just interesting pattern strategies, let's look at an actual piece of code here, which I have a vector3 class, and just kind of iteratively see if we can make it faster, or the experiments that we want to do here. So again, I try to put myself in the mind of a programmer, and this is something I'm guilty of doing, and this might be perfectly fine, honestly. But I have a structure here, vec3 or vec n, so it can hold n number of elements, sort of like the mathematical vector. So I'm going to store all of its storage in these components here, and that's basically all I wanted to do, just store a list of numbers. Okay, and again, we would use these in vector math, for instance. And then we might want to, construct this vector, print out the elements, and then maybe add it with another vector. Okay, so that's all the classes, and that's what we want to work with, or this data type. It's templated, so we can work with any type of data, integers, floats, doubles, or whatever, and that's what we're going to work on. So with that in mind, as I'm implementing this, I want to talk about a first strategy, and we saw a little bit of this strategy before, but let's see if we can identify it in the wild. All right, so we saw this with Fibonacci, maybe an idea of saving values. But this is the idea of caching here. So again, we're going to trade some space by storing something in memory and trading, hopefully gaining runtime. Okay, so I've gone ahead and implemented 3 members here. The first one's the constructor, don't have to worry about that. But these second 2, I'll tell you, are interesting. And I might need help from my front row who can read it, probably the clearest from the classroom. But does anyone spot somewhere where I'm potentially recomputing something over and over and over again? I say potentially because it depends on our... Yeah, I heard size. I'll take it because that's the answer I want. But let me highlight it for folks. There it is. I'm computing the size of vector every time, dot size. Okay. Now, if we actually look at the standard template library, maybe size is actually just stored as some value. So we need to think about, is that expensive or not? But at the very least, it is a function call that we have to look at. And in a more interesting example, maybe this is a graph or some other data structure that's more interesting to traverse, right? So if we have to recompute size, maybe that's really expensive. Okay, so let's at least look at it, identify it, and see if this will make our code faster if we can just cache that value. Okay, so again, what does it mean to cache this value? Well, from the example here, line 33, I'm just saying, well, okay, I'm just going to compute the size one time and store it. Okay. Now, how meaningful this is? Maybe if you have a really big vector with 1,000 elements or whatever, might be more meaningful. In my example, I'm using 3 because that's what a lot of game programmers use for X, Y, and Z. Maybe not as meaningful. Okay, so we have to know our problem in order to solve it here. And again, as I mentioned, pragmatically, if we have a graph or something, this becomes a little bit more interesting, but still interesting nonetheless, because we want this to be fast. Yeah, question.
Why don't we read off totally on the side issue for each group so see what class then?
So the question was, why don't we read off each size? Oh, with a for each? Yeah. Yeah, because I see. So the question is, why don't we use for each? Because especially for print or something, right? We just want to use a range-based loop. We want to look at everything. One part efficiency for this code. With a range, it makes it a little bit harder for me to show you one of the other optimizations. So this is in parts for simplicity here, to just iterate through a for loop. Yeah. Is there a follow-up on that? Yeah.
Actually, by looking at it, the very first thing I would do is to add the size that is displayed targeting.
Okay.
If I do this, I enable the loop unrolling at the compiler level.
Yeah. All right.
And also, like, I would pass the vector to the data.
Yeah.
I would like store it in the stack or in the page.
Okay. Let's see. So there are a few comments, and I've got to be careful here because I know I'm standing between you folks and lunch. But there are a few comments about, and let me try to go in order because it's almost the same order I might go in, on templates. Something about loop unrolling. And then something about, hey, maybe vector is not the right data structure here. Okay. Did you look at my slides? All right. Yeah. so let's keep this in mind. Let me try to again walk us through here and see, what's going to be fast here. All right. So I do have to give you some tools to measure this for our optimizations. So one tool you can just use if you're on Linux or any command line is there's some sort of time tool. So you can just run the program and grab the time. You get the real time, which is like looking at the clock, a user time, which is again the actual time on the CPU, and then the system time when the operating system's doing something. But for the most part, I'm just looking at the user time here. No optimizations, 0.025 seconds. This is running on like 1 million iterations of adding some vectors together. The caching a bit faster, but again, this is a small example. It might be noisy, so we want to keep looking at this until we're pretty sure we've got something that's faster. Okay, if you run this, I tried to gain 10 samples or so, but there's a lot of things we have to think about to really being convinced this is faster every single time. Okay, so let's see if we can figure out some more. And we really want some better information than time, especially to convince ourselves that, yeah, we reduced something, or is this just noise, right? I've got like 20 tabs open on Chrome. Is there just noise from the internet disturbing these tests? Maybe. So we want an actual better profiler that'll give us some more detailed instructions. So in particular on Linux, I'm using perf. Just by a show of hands, how many folks have used a profiler before? I'm getting about 50% or so. That's great. And for those of you folks who haven't, use a profiler or use a debugger. Leave it always on, like that game development talk we had. So let's look at what perf gives us. And again, I'll try to read off the highlights if it's a little bit small for you, and you can look at the slides later. But what I want to see here are things like how many instructions were actually executed. Other things that might be interesting, like how often we're branching or jumping around. And oftentimes, the other thing we'll want to look at is how well the cache is doing on the hardware, cache hits and cache misses. Okay, so from this output, the top level diagram with no optimizations, it is running more cycles, so our CPU is perhaps doing more work. There's more instructions being executed. There are more branches or jumping around, and there appear to be less branch misses, which is kind of interesting. And we'll kind of have to think about why that is, or I can revisit that, but we are storing something in memory, and loops want to do the most predictable things, so that could be a hint. So at least I'm convinced there's less instructions being executed, so that seems like a win to me with this optimization here. But again, we have to decide, was this even the right place for us to spend some time? So again, this is getting into some of the, again, Knuth stuff from the start of the talk here, thinking about, should I have complicated my code? Is some other developer going to come in here and see like, hey, why was Mike, just putting little storing length every time? Okay, maybe there's a better strategy than that. So the cool thing about profilers like perf for, the half of the room, to check out is you can see where you're actually spending time in your program. So taking a look at this, and it's kind of interesting because you also have to be careful looking at these profiles, but on the no optimization path here, I'm taking 39% of my time doing plus equals, which is where I'm doing the add. That's what I was trying to optimize. On my cached example, I am spending 54% of my time there. I say, hey, that's more. Why is it more? Well, again, we're calling size a lot from this other function. So sometimes we have to look in the methods within. Sometimes you get what's called a call tree as well, which can help you visualize this stuff. Okay, so you sort of have to add the total of the operations that you're doing, at least for this micro benchmark. All right, so was caching a win? I declared a win in some regard here, that we're doing less instructions. It generally ran faster. So that's probably a good idea. And maybe this is a strategy that we want to try again on different data structures like graphs or maybe things that aren't integers, bigger objects, and so on. Okay. But one of your colleagues in the audience here said, hey, I'm not, satisfied with that. And these could be little things that you pick up from, say, the standard template library, like you might see hanging around, like why are we even storing length here? Okay. So what I actually want to do here is make a trade-off and not even have to worry about caching that value for length, because at least for the requirements of this class, and again, we have to define the problem. Is this vector ever going to resize? I'm saying no right now, okay? I'm a game developer. We're going to have worlds with X, Y, and Z. That's 3 coordinates, so it's going to stay that way, okay? Now, of course, if it is going to change sizes, we might want to think about that. But since it's not, it's a sort of static in size. Again, we can use our templates, which around line 7 here, you'll see. I'm just going to add another template parameter for length. And you'll see this in the standard template library with std array, okay, where you can store the length, for example. All right, so we can learn from some other folks' code. And then, so that's the update. Again, we're just adding a second template parameter for length here. And here's the results here. Did this improve our program here? So the answer is yes, it did improve it. And this is our fastest result yet. Okay, so we've gone down in cycles. There's less instructions being executed, less branches, and now this time, we're not getting weird branch misses. Okay, because we're just storing the actual length. It's just a value now. It's not something we have to look up in memory. So that's a big win here. Okay. Okay, so that gets us into strategy number 3. Which is right on cue with our colleague here, is saying, were we solving the right problem here with the right data structure? I kind of took a guess because everyone just says, hey, use vector, or that's the thing I know about most, right? So it's a good default to start with. So do I really need the capabilities of a vector if now that I'm saying the size is going to be static here? So I kind of, again, this is just sort of thinking through the process here. And again, my note that I'm changing the problem here a little bit and saying, yeah, this is a fixed size data structure now. So let's just make this our type here, just a static array, or excuse me, a fixed size array here. Okay, that's going to be stack allocated. Okay, so let's see how we do with that. We've gotten rid of a dependency as well, a vector, so that's nice. And fastest yet. Okay, so faster again. And at this point, we're getting into like 0.006 milliseconds. So now I'm pretty convinced that at least there's something here with this choosing a better data structure. Okay, and that's almost always a win here. When you're thinking about optimizations, do you have the right data structure before you start doing these little, I'm going to put a little micro optimization here and a code motion because Mike taught me about that and hoist this thing, right? Think about the actual data structure for the problem you're trying to solve. Now I've chosen a different data structure here, but this is still bothering me a little bit in the sense that I am spending, still a significant portion of my program here, 79% of my time in this plus equals. Now maybe I'm just doing a lot of work there. That's okay. But are there other things that we could change here to try to speed things up? And I've got a little aside here if you thought I was cheating by this time keep allocating an array here, and you can see it's a little bit slower. So again, try to stack allocate things. It's another architecture thing. But let me get into optimization number 4 here, which is this time thinking about specialization. So I know the task that I want to do. I know I'm adding a lot of vectors together here. So can I, where I was spending 79% of my time in my program, can I make that really fast? So now maybe I can start doing the little bit tweaks and moving values around and trying clever tricks. And what it means to specialize a function, or oftentimes I'm talking about template specialization. So I'm saying I have a specific use case here. This could be for any function, but for our vector example specifically, I'm saying, okay, if I'm someone who's using vectors with X, Y, and Z, 3 components a lot, can I make that use case very fast? So the answer is to write a template specialization. So again, in C++, you can look at this example later, where I just have a vector with int is the first parameter and the length 3, okay, if you haven't seen that before. And what do I actually do in this template specialization to try to speed things up? Well, again, I just try to grab some of my knowledge from, how do I make things faster? I can get rid of the loop. I can unroll the loop because I know I'm working with exactly 3 things and just make the simplest possible code. Okay, make it the easiest possible thing the computer can think about. So unrolling a loop. Okay. So with that example, I get relatively good results. Now for this particular benchmark, it's not always going faster because I suspect there's a little bit of noise here, right? It's executing pretty quick. Okay, so maybe lengthen these benchmarks, try it on a different data structure to see if that pays off for you. But in general, I'm getting pretty fast results as well here. There are some other interesting things here, though, because I did pay something for that specialization. I paid in terms of space of my code size, right, as I'm adding more templates here, which is rearranging my code layout and things as well. So again, there's always something going on. So let's continue thinking about some of these optimizations we can do here. And I'm going to, again, maybe change the problem a little bit here and say, well, what if that vector was really important? And I do want to be able to change the size of things, because now, it's possible that I'm in some, data science application. I can have vectors that grow and scale as new data comes in. So something that we can do here is to set up our actual data structures in multiple phases. The most common type of optimization where I see this with is, again, with the vector, where if I know what the length is here, again, so I can kind of keep that length attribute here, I could still pre-allocate it, meaning by just calling dot reserve or dot resize on that vector to initialize it as a full vector. Okay, have folks seen this optimization before? What about dot reserve? A few folks do, yeah. What's the cost when I'm doing a pushback in a vector? Well, I'm allocating some data, putting data in if there's room for it until I can't, and then I've got to stop, redouble the actual vector, copy everything over, and then I can push in an element, right? So in this way, I can, at least on my initialization, maybe speed things up a little bit, okay? And what might happen too is if I end up just not needing this vector here, and I've sort of set it up in all different stages, maybe you can save some work later on in the road. Okay, so I mean, those are a couple different examples taking on this journey with what do I need to do with this vector and some different optimizations that we can do with it. And we've played around with caching, compile time computation by putting in a template parameter, specialization with the loop unrolling. We changed our actual data structure once we knew what problem we were going to solve. And then there's other things like multi-phase initialization. But there's still yet more techniques that we have available for us. So just a few more patterns or strategies, things that you can think about. If I'm going to give a second round of this talk later, these are the things to focus on. Are there things that we can hint to our application which are actually running? And there's some interesting examples actually in CPP reference for in place back, or the in place example with a map of just trying to find, the next location where you're going to do some insertion. Okay, so something that could speed you up. Pre-computation, we've touched on this a little bit with using templates, but we can push this pretty far with some things like const expr, for instance, template metaprogramming, again, trying to compute results for us at compile time, or even just loading a file or just baking in data into a header. So we have a bunch of results already ready, right? If you're going to compute the Fibonacci sequence, why not give yourself the first, 40 values just in your code or whatever you need. Other interesting strategies, lazy versus eager evaluation. Eager evaluation, again, when you call a function, means just execute. Lazy meaning you can defer the computation. So we see this with things like std async as a good example. Copy on write, which would be an example of anytime you make a copy, you don't actually need to save or create that copy until you change the values. And then you have other things like short circuit evaluation and reordering the evaluation of getting an early exit, essentially. Batching, again, if you're a graphics person, having just one draw call to draw everything versus a bunch of individual calls. We see this also, if you're not a graphics person, all the time with just buffered output when you're just writing out text to your screen. That's another sort of batching operation. Hashing values, so if you have long strings and you want to compare them, comparing the hash instead of actually the character. Again, just some general strategies to get you excited about other stuff if you already knew these things, and give you some categories where you can look. So, as I'm kind of wrapping this up, performance can be a little bit tricky. There can be a little bit of noise. Running a proper experiment takes some care. Right, so we'll want to take some of these micro benchmarks that you've learned about and increase the size or put them in real workloads to see how they actually work. And there's actually some lore in the performance world. I don't know if folks have heard this, but I linked to Stack Overflow, where there are many cases before folks putting a printf in their code and it got 10% faster. And I say, oh, wow. And again, just sometimes putting the right instruction in the right place makes things sort of reorganized in the right way. You get a lot of speed. So I've heard this for a decade now, and these kind of posts pop up, which is fun. So with that said, that's all for now. There's still a lot more we can do for this. Optimization's really, really fun, in my opinion, because you can measure and see your results. There's not really patterns, but again, strategies or trade-offs when it comes to optimizing. And, again, folks should actually read this paper. Then, next time someone says, premature optimization is the root of all evil, you can say, but the next, party you're at or something. All right. So thanks for having me, folks. I'll take questions or stick around. And if no questions, I know there is lunch coming up. So, but yeah, a question. Yeah, go for it. I'll repeat it.
I tried also to measure the impact of making a reserve and a pushback against using the plain, let's say, array, because I'm expecting they to be somewhat comparable.
Yeah, the question was about comparing vector with reserve and then pushback versus the array. I have tried this before. I have done this. The difference is very close usually because you're pre-allocating. Where you might be paying for it, since those allocations are happening on the heap, for instance, with the vector, the memory accesses later might cost you more if they're not on the stack. But if you needed a data structure that's going to extend, that's your only choice, and it's as good as you can get. Yep, thank you. Another question? Yeah.
Some micro-optimization are quite generally useful and take advantages. Other can be dependent on the compiler, on the architecture. So are there strategies or consideration to take advantage of this, or detect that in the next version of the compiler we lose something because of that micro-optimization?
Yeah, so the question was about different compilers and architectures are changing, right? If you're developing for a PlayStation versus a desktop, the same optimizations might not always work, and it's a moving environment. So what are strategies we can take to try to determine, like, was this a good optimization to put in our code? There are some neat tools you can do to try to do things for the executables that you're making, things like random address layouts for your executables. So it's not dependent on like code order or some of those things. Some of these things are just knowing your hardware. Like if you know the actual cache size and setting up your data structures for that, that can be a big win. So I've seen code bases where you just know how many levels of cache there are, what the exact cache size is. Now that becomes a little bit of a nightmare maintaining and updating your code. Some folks will go to the extreme to manage that. But otherwise, I think it's just sort of measure, and try to have the best possible use case. I'll give you another interesting antidote, which is to take you down the road of profile guided optimizations, which is running your program, getting a profile of literally how many times each line executed, perhaps. And then you can actually feed that back in the compiler and it'll try to rearrange things in an optimal way. The reality is if you have something very dynamic, like an application that's changing a lot or a game, sometimes you just don't get big wins from it. So in a sense, what I'm saying is you might end up just picking the lowest common denominator optimizations that work well across the board. So thank you. All right, thank you. Got the call for lunch.